So in question number 1, you've got 3 forces acting. You've got a charged rod, so basically it's pulling in this direction. You've got the weight of the sphere down and the tension. So these 4 show free body diagrams for the sphere. However, the tricky bit is to try and figure out the relationship between the force sizes. To do this, let's resolve horizontally and vertically. So the tension in the string I'm going to label T, the force pulling the sphere this way, S, and the weight is mg. If I resolve horizontally, if this is angle theta, I can see that S in this direction is equal to T cosine theta, which I've expressed here. In the vertical direction, I can see that weight, mg, is equal to T sine of theta up. So what does this tell us about sizes? Well, if T has to be multiplied by cosine theta, which is always going to be less than 1, then T must be greater than S. Similarly, if T has to be multiplied by sine of the angle, which is always going to be less than 1, then T must be greater than the weight. So therefore, we need a diagram which shows that T is the larger force. Now, how do we know that it's not C? Well, if we imagine a situation where the weight was that small, you can probably quite easily imagine how S would be the much greater impact, and this angle would be much smaller. Okay, so an angle of approximately 45, because that's what it looks like, it needs to be kind of relatively balanced in terms of the effect of these two. So that answer is a little bit of a perception one, and understanding the effect of the horizontal and the vertical accordingly. This question is very similar. We have weight, force, and we have a situation of equilibrium. Now we need to look at the relationship between F and W. So again, I'm going to resolve the forces. This time I'm going to do it only vertically, because horizontally we'd end up with an expression with just F. So if I resolve vertically, you can see that the weight down is equal to the force component in the vertical direction, which would be F sine theta. But there's 2, so it's 2 times F sine theta, which means that F, or better still, 2F times sine theta, which is less than 1, would give you W. And that tells you that 2F is then greater than weight. So the answer is A. Okay, so there are 3 forces acting here. You've got weight hanging from the center of this bar, and you've got the 2 tension forces. You're given an angle here which hasn't come out, so I'll draw it in. Now, which of the following is equal to tension? So, using the free body diagram for the bar in the center, let's resolve vertically. And as you can see, the answer is B. This is our free body diagram for the bar. And you can see the weight is equal to T sine of this angle. But of course, this angle here is 90 minus theta. So, resolving, we get weight equals 2 times T sine theta, which is equal to, we're going to change this expression, simplify it, to cosine of the angle. So we now have weight equals 2T cosine theta, and we rearrange to give us our answer B. So the inclusion of this question is a little bit unfair because this is actually a circular motion question, which is topic 5. I'll go over it anyway, just because it could be useful. When an object's moving in a circle, it's not in equilibrium because its velocity is changing continuously, and that means that it's accelerating. And as you know from Newton's second law, force is proportional to acceleration. So if something is accelerating simply because it's changing direction, not because it's changing velocity, magnitude, sorry. So the velocity is changing in direction, therefore it must be accelerating. Therefore there must be a resultant force. And it's a little factoid, but the force that makes an object move in a circle is always towards the center of that circle. So the correct answer is B. Because as you can see, and this is a good equilibrium question, the actual force towards the center of this circle, if we resolve horizontally, is F sine of that angle. Okay, so don't worry if you didn't get that one right. And you didn't have to do this one either because we haven't quite got there yet. This question is pretty relevant to forces, but still worth doing because it's the kind of IB question that you get quite often, which is a composite. We have a solar propulsion engine, which is ionizing xenon and accelerates them. So these xenon ions are forced out that way, and because of Newton's third law, if you force these xenon ions that way, there is an equal and opposite force in the other direction, a little bit like your balloon rockets. The ions are ejected with a speed of 3 times 10 to the 4. So for part C, we ignore part B because we haven't done that yet. If you've got 81 kilograms of xenon and the mass of one ion is 2.2 times 10 to the minus 25, then if you divide 81 by the mass of 1, so you've got the total mass divided by the mass of 1, you will end up calculating the number of xenon ions. Okay, and as you can see, you've got 3.68 times 10 to the 26 in total. Now, if every second 77 times 10 to the 18 xenon ions are leaving this point, then if you divide this by 77 times 10 to the 18, you will get 7.78 times 10 to the 7. Okay, now what you've worked out there is the number of seconds that your propulsion will work for, okay, because you've got the total number of ions and now how long that's going to last. But you don't want it in seconds, you want it in years because the answer is 1.5 years. So you now divide that number by 3.2 times 10 to the 7 and it should give you 1.5 years. 3.2 times 10 to the 7 being the amount of seconds in 1 year. Okay, this following one is horrific, but it is a forces question. So if you couldn't do it at the time, don't worry, but see if you can work through the logic. This question is about Newton's third law. So if you have, it's asking you for the initial acceleration of the spaceship. Now we know that force equals mass times acceleration. So we need to find the acceleration of the spaceship and the mass. So what do we know? We know that the rocket is moving that way because the xenon is moving this way. Now, so if you can work out the mass times acceleration in this direction, you can work out the mass times acceleration in that direction. Those forces should be equal and opposite. So let's work out the acceleration first. Now, the mass of the xenon that leaves the rocket in 1 second, and that's actually an important fact, is going to be equal to 7.7 times 10 to the 18, that's given in the previous question. That's the number of xenon ions leaving the rocket, times the mass of one xenon ion. So this will give you the mass of xenon leaving. Now let's think about the acceleration. The xenon was quite happily sitting in here, not moving at all with respect to the rocket. So its initial velocity is 0. And then 1 second later, its velocity was 3 times 10 to the 4. And that's given in the question. So the change in velocity is 3 times 10 to the 4 per second divided by 1. So the acceleration is 3 times 10 to the 4 meters per second squared. So now we have our mass. We're going to work out acceleration. It's 3 times 10 to the 4. Okay, now this gives us the force of the xenon out, which should be equal to the force felt by the rocket due to the xenon. So let's now work out what the acceleration is. The force on the rocket is the answer to this. Okay, and that's going to be equal to mass times acceleration of the rocket. So if we work out this first, we get 5.1 times 10 to the minus 2 newtons. That's the force of the xenon out, and that's equal now to the mass of the rocket times its acceleration. Now the mass of the rocket is the mass of the fuel, which is 81 kilograms, because remember it was full, it wasn't an empty rocket, plus 540 newtons, which is the mass of the rocket itself. So if we now divide this number by this, you should get the value 8.2 times 10 to the minus 5. So I'm going to do part E on this page, because if I go forward, I can't come back to the graph, and I'm going to need the graph for question F. So question E asks why the acceleration of a spaceship is increasing with time. Now you know that F equals ma. So if the acceleration is increasing, it's because the force is increasing or the mass is decreasing. Now the force can't increase because the force depends on the mass of xenon leaving the rocket, and that's constant. So there has to be a decrease in mass. So you've got a rocket filled with fuel. Can you think of a reason why its mass would decrease? Hopefully you figured it out now. But as the fuel gets used, then the actual fuel inside the rocket decreases. So therefore the mass of the rocket plus the fuel decreases. Now it seems almost like a trick question, but there you go. Now let's go on to F. So in F, you have to use the data from the graph to work out the speed of the spaceship when it runs out of fuel, which is here at 4.8 times 10 to the 7 seconds. Now in order to answer this question, you really need to understand what's going on with the spaceship. So let's look at that. At time equals 0 at the beginning, when the engine is just switched on and the xenon is released, you have an acceleration, an initial acceleration of 8.2 times 10 to the minus 5. And this was worked out in a previous question. The velocity at that point, just as that engine is switched on, is 1.2 times 10 to the 3. So you're starting off at this speed, and your speed is increasing due to this acceleration. So it's not increasing linearly, it's continuously increasing because of this acceleration. Or should I say acceleration change, which happens between time equals 0 all the way through to time equals 4.8 times 10 to the 7, obviously. Okay, so how do we solve this question? Well, we know for a fact, or I hope you know, that an acceleration time graph would give us the speed, the increase in speed, by working out the area under the graph. But this graph starts at 8. In fact, that's an error. There's a mistake in the question. We know that beginning acceleration is 8.2, so really that should say 8.2, so that's a mistake in the question. So going back to how to work this out, we don't have an origin of 0. So basically we have to visualize the graph in this way. Your acceleration time graph should actually look more like this. And the area under the graph would be all of this. So in order to work out the increase in velocity from t equals 0 to t equals 4.8 times 10 to the 7, you would work out the area under this entire shape. So what we have here is a triangle and a rectangle. So let's try and work out the area of this triangle first. And that triangle would be this height here, which is 9.45 minus 8.2 times 10 to the minus 5, well that's that side, times 4.8 times 10 to the 7, which is this side of the triangle, and then divided by 2, which is a triangle. So let's see what that comes out to be. Okay, that should be 300 meters per second. But there should be a decimal point. I don't know why I wrote a multiplication sign. It's 4.8. Okay, so that's 300, but that's the triangle. So now we need to work out the area of this rectangle here. So let's calculate that. So we have this time 4.8 times 10 to the 7, which is that side, times the height, which is 8.2 times 10 to the minus 5. And that gives us, there you go, so that's 3,936. And if we add those two, we end up with, so plus 300, we end up with 4,000, won't let me move it, oops, put that there, we end up with 4,236 meters per second. But of course, that's not the starting speed. The initial speed of the spaceship was 1.2 times 10 to the 3. So we now need to add that to this because this is now in addition to that. So let's add 1.2 times 10 to the 3. And our final answer is 5,000. So we can squeeze that in because I can't make room for it now. In fact, let's round it up. 5.4 times 10 to the 3 meters per second, or s to the minus 1. Let me rub that off and write it properly. ms minus 1. So that is a really tricky question. But the more of these types of questions that you work through and you do, the better your problem solving skills will become. Okay, and that's it till the next formative.